Okay, friends, welcome to your Business Calculus Lesson 5.1, Marginal Analysis and Other Applications. If you'll recall, we talked about cost functions previously, and usually we worked with a linear cost function, but cost functions can be other types of functions. And remember, it's going to give us the cost as a function of the number of items and produced, and that's going to be X. So the marginal cost is always going to be the first derivative of the cost function, which makes sense when we think back to uh, our linear cost models. Our marginal cost there was the slope, which would be the first derivative of that function. So the interpretation here is that the first derivative, or c prime of x, is the approximate cost of producing one more item. The average cost, if you'll recall, is given by the cost of x items divided by x, how many items you have. Okay, the same things can be done for profit and revenue. So remember, revenue is your total income as a function of the number of items. And so the marginal revenue function is going to be the first derivative of that revenue function, and it is the approximate extra revenue from the sale of one more item. All right, remember, usually you're given the cost function. You can figure out the revenue function from the price. And then the profit function we get by taking the revenue function and subtracting the cost function. So the amount of money we bring in minus the amount of money we had to pay to actually create the items. So marginal profit, much like marginal cost and marginal revenue, is going to be the first derivative of the profit function, where p prime of x is the approximate extra profit from the sale of one more item. So p of x is often a parabola with a maximum that shows us what the maximum possible profit is. We find that maximum by evaluating when p prime of x is equal to 0, when the marginal profit function is equal to 0. So when we solve that, we get x values, or an x value that tells us how many items are needed to maximize the profit. And then when we take that x value and plug it back into our profit function, our p of x, that tells us what that profit will be. Okay, so here's an example. A widget manufacturer that determines the demand function for her widgets is little p, so that's the price. Be careful. There's the profit function, which is capital P of x. This is little p, it's the price, okay, is 1,000 divided by the square root of x. So that's how the manufacturer knows how many items to produce if a certain price is desired, where x is the demand for widgets at a given price p. The cost of producing x widgets is given by the following cost function. C of x is equal to 10 times x plus 100 times square root of x. Remember, square root of x can be written as x to the 1/2. And so when we're finding the derivative in a minute, we can still use the power rule on that term, plus 10,000. Determine the marginal cost, the marginal revenue, and marginal profit at x equals 100 widgets. All right, so for marginal cost, we're going to find the first derivative of our cost function, and then we'll evaluate for x equals 100. So the first derivative of 10x is 10. Of 100 times the square root of x is going to be 50 over the square root of x, and those are both by the power rule. And then 10,000 is a constant, and so the first derivative of that is going to be 0. It never changes. So now we need to evaluate that first derivative at 100. So we plug in 100 for x, and we get 10 plus 50 over the square root of 100. So that's going to be 10 plus 5. So we get 15. So that means the marginal cost at x equals 100 is $15. This is the approximate cost of producing that 101st widget. Let's do the same thing for revenue. So if you'll remember, revenue equals the number of items sold, x, times the price, p. All right, so we're using our demand function here because that gave us a function in terms of x for our price. And we're going to have x times p, which is x times 1,000 over the square root of x. If we rationalize our denominator, we're going to multiply on top and bottom by the square root of x, and that's going to give us 1,000x times the square root of x over x. We can cancel the x's, and we get 1,000 square root of x. Whew. So that is the revenue function. Now we need to take the first derivative of that. So we want to think of square root of x as x to the 1/2. And so we'll apply the power rule, and that'll give us half of 1,000, so 500 times x to the 1/2 minus 1, so negative 1/2. So that's going to be 1 over square root of x. So we get 500 over square root of x. We want to plug in 100 because that's our amount of interest. We want to know about 100 widgets. And so we get 500 divided by 10, and so we get 50. Thus, the approximate revenue from selling the 101st widget is $50. Okay, marginal profit is going to be the first derivative of our profit function. Our profit function is going to be the revenue function minus the cost function. So we have 1,000 times square root of x minus, and remember you have to use parentheses here, our entire cost function. We combine terms and we get negative 10x plus 900 square root of x minus 10,000. So in order to find that marginal profit, we have to take the first derivative here. And so negative 10x is going to have negative 10 as its derivative. 900 times square root of x is going to have 450 over square root of x as its first derivative. And again, the constant has a first derivative of 0, so we don't even need to show that term. Now we need to evaluate at 100. So our p prime of 100 is going to equal the negative 10 plus 450 over square root of 100. So that's going to be negative 10 plus 45, or 35. So selling the 101st widget brings in an approximate profit of $35. Now, the other application we're going to look at today involves position, velocity, and acceleration. If s of t is the function that gives the position of an object at time t, then v of t, which is the first derivative of s of t, first derivative of the position, is going to be the instantaneous change of the position, which is going to give us velocity. Acceleration, which is the instantaneous rate of change of velocity, is going to be the first derivative of the velocity function, which means it's the second derivative of the position function. Okay, so if a stone is thrown up at 10 meters per second from a height of 100 meters above the surface of the moon, its height in meters after 10 seconds is given by s of t equals 100 plus 10t minus 0.8 t squared. So we want to know what is the average velocity after the first 4 seconds the rock has been thrown, what's the instantaneous velocity of the stone at t equals 4, and then what is the acceleration. All right, so your average velocity is going to be your change in position divided by your change in time. So you're going to take the position function and you're going to plug in 4, and that's what we have here in these parentheses. And then we're going to subtract off the position at time 0. Well, if you plug in 0 for t, you're just going to be left with 100. And when you evaluate that, you get 27.2. Then we're going to do our change in t. So it's going to be 4 seconds minus 0 seconds. So that's 4. And so we get 6.8 meters per second. So that's the average velocity during those 4 seconds. So let's see what the instantaneous velocity is at t equals 4. So we need to get our velocity function. So that's the first derivative of our position function. And so the 100 is a constant. So it's going to contribute a term of 0, which we don't even need to write down. 10t, it has the first derivative of 10, and then negative 0.8t squared by the power rule has a derivative of negative 1.6 and t to the first, or just t. All right, so if we want to know the instantaneous velocity at a particular time, we just plug that into this formula. And so we're going to get 10 minus 1.6 times 4, which is going to be 3.6 meters per second. All right, if we want to know the acceleration, acceleration is equal to the first derivative of the velocity function, which is equal to the second derivative of the position function. So if you look back at our velocity function, it was 10 minus 1.6t. So the 10 has a derivative of 0, and negative 1.6t has a derivative of negative 1.6. And so that is negative 1.6 meters per second squared. Okay, awesome. So go ahead and print out your problem set, start what you can, and come see me if you need some extra help. Thank you for watching the video, and I will see you in class. Have a great day.